Okay, we are going to look at a different way of solving problems involving dynamical systems today called work energy methodology. The way work energy methodology works is you still start with Newton's second law, F equals ma, and unlike what we did in the last time, we looked at a set of problems involving what is called the impulse momentum approach. In the impulse momentum approach, we take Newton's second law and do a time integration from some initial time t1 to a final time t2. What we find is that the impulse, which is the integral of the force over the duration of time, is equal to the actual change in the momentum. So, we are going to do the same thing, except instead of integrating in time, we want to look at an integration in space. So, for example, if I have a force whose variation I know spatially, not necessarily with time, how would I take advantage of the known variation of the force with respect to a spatial coordinate and understand the dynamics of a body. Alright, so with this is going to be called work energy formulation. The basic principle is as follows: you still start with Newton's second law, and let us say in a general case f is some function of a spatial coordinate. For that situation, I do an integration of this from some initial location of the body x1 to a final location of the body x2, and do the same thing on the right hand side. Now, let us look at the right hand side first. Acceleration a dx can be written as dv dt times dx, which is nothing but the rate of change of velocity integrated over some infinitesimal distance dx. Now, this is not exactly correct, but it is a convenient way to understand the basic transformation. So, from here we can write this as dv times dx dt. Now, the logic here is as follows: if v dv is essentially dx dt times dv, dv being a rate of the net change in the velocity over some change in the independent coordinate. So, if I replace this a dx with v dv, what we end up finding is that this is equal to half m v2 squared minus half m v1 squared, where v1 is the velocity at x1 and v2 is the velocity at x2. So, the right hand side of this equation is simply the actual change in the kinetic energy. Okay, v2 half m v2 squared is ke2 minus ke1. The left hand side, on the other hand, is essentially the integral of a spatially varying force with respect to x from some initial location x1 to x2, and this is what we are used to understanding as the work done on the body. Okay. So, Newton's second law in a weaker form written in a spatial coordinate essentially amounts to saying that the work done on a body between two spatial locations x1 to x2 is exactly equal to the net change in the kinetic energy of the body between those two states. Alright. So, we are going to put this to some test here. Let us take an example problem. We have a block whose weight is 64 newtons, that is falling in a gravitational field. Okay. Its initial velocity at some xi equal to 0 is known to be 4 meters per second, and at some final location when the center of mass of this body is now at this location xf equals 1 meter, we are asked to find the actual velocity of that body. Now, gravitational force is going to accelerate this body from xi equal to 0 to xi equal to 1. We also have another force f of x whose magnitude goes as 128 times x, 128 times x being the actual location of this body. So, meaning when the body is at this point, there is no force acting on this body, and as the body moves downwards, as x increases, the magnitude of the force increases and its direction is always opposing the motion of this body. So, this is a very simple model of a body falling on a little spring or a cushion. Okay. We are asked to find the velocity when the body is at 1 meters. All right. So, let us draw a free body diagram of this body first. The weight is acting on this body, that is magnitude 64 newtons. At any x location, the force acting on this is 128 x and it is opposite. Okay, there are no other forces acting on this body. So, at any given instant of time or at any given x location, the sum total force acting on this body is, I am going to take downwards positive as my convention, is 64 minus 128 x. This is the net force acting on this body at any instant of time, at any x location, at any position of this body. We only know the force as a function of position on the body, position of the body. Right. So, now I do know that between x1 to x2, this f of x dx is equal to half m v2 squared minus half m v1 squared. We are told v1 is 4 meters per second, v2 is an unknown, we are asked to find what v2 would be. Okay. So, let us do this integration between x1 equal to 0 and x2 equal to 1. So, integral 0 to 1, 64 minus 128 x dx, the actual work done is equal to that. Let us compute that first. This is integral 0 to 1 64 dx minus integral 0 to 1 128 x dx. This is simply 64 times 1 minus 0 minus 128 times x squared over 2 evaluated in the limits 0 to 1. So, this is 64 minus 64. Which is 0. So, the actual work done on this body is 0, which also should mean half m v2 squared minus half m v1 squared is equal to 0. Now, we do not know v2, but we do know v1, which implies v2 squared equals v1 squared. If v2 is unknown, v1 is 4. What we do know is v2 is plus or minus 4 meters per second. So, there is two possibilities for the actual velocity at this location. I'll call this location 2 in relation to this being location 1. The body is here. When the body is here, it is either moving down at 4 meters per second or it could be moving up at 4 meters per second. Okay, so let's, in order to really understand what's happening here, let's do this in a slightly more generalized way, and that will help us understand this. I want to do this without setting a number for x2. I am going to do this in a symbolic fashion. I am going to let x2 be any location x. So, w is integral 0 to x 64 minus 128 x dx. Let us go through and integrate that. So, that gives me 64 x minus 128 x squared over 2, which is 64 x times 1 minus x. Okay. So, half m v2 squared minus half m v1 squared equals 64 x times 1 minus x, that is what we just found. So, v2 being v at any location x. So, I will write it as v squared minus half times 64 divided by 10. I am going to take g to be 10 meters per second squared, not going to complicate the numbers. v1 is 4 squared equals 64 x times 1 minus x. Okay. So, I am going to replace the m here as well with the same 64 over 10. So, what I do know is that v squared minus 16 equals 64 divided by 3.2 x into 1 minus x. Or v squared minus 16 equals 20 x into 1 minus x. V squared equals 16 plus 20 x minus 20 x squared. So, if I plot v as a function of x, you will notice that when the right hand side goes to 0, v equals 0, and when the right hand side goes to when the right hand side is 1 or 0, v equals plus or minus 4. Okay. So, essentially what we find is that if I plot the velocity as a function of x, it takes on a number 4 at x equal to 0, and at x equal to 1. So, initially the velocity increases and then decreases. So, you can notice that the velocity here would be maximum when this right hand side is, when the derivative of this right hand side is 0. Okay, so, that would be roughly at about x equal to half, that would be at x equal to half. Now, past this point it becomes 0 and then further increases back again. So, essentially the force that is opposing the motion of this body in a downward direction, which is of magnitude 128 times x, has two possibilities. So, this is not exactly correct. So, when in the downward trajectory, the velocity essentially increases till about half and then decreases down to 1, and at some other location it goes to 0, at which point the velocity changes sign and starts to rebound back up again. So, you would get a curve that looks like this. Let me complete it. it would be symmetric about the horizontal axis. So, at this point it would come back to being minus 4, meaning if this was 4 in the downward direction, this is minus 4, meaning it's the block would be moving in the upward direction. At some location past the 1 meter mark, the body would come to rest and then rebound back up again. When it rebounds, when it passes the 1 meter mark, it would be moving with the same velocity of minus 4, and then at the same half a meter mark it would have the maximum negative velocity, meaning maximum upward moving velocity, and then come back up to a minus 4 velocity, come back up to 4 meters per second, but in the upward direction when it comes to x equal to 0. The actual location of this, I will call x naught, can be found by taking the root of this equation 16 plus 20x minus 20x squared. So, let us do that. So, if I divide this by 4, we get this to be 4 plus 5x minus 5x squared equal to 0. So, the x naught is plus 5 plus or minus root of 25 plus 100 divided by 10. So, 1 plus square root of 5 divided by 2 is one possibility, and I will call this x naught 1. X naught 1 is 1 plus square root of 5 divided by 2. The other possibility is 1 minus square root of 5 divided by 2 meters. If you look at these two numbers, this is past x equals 1 meter, this is actually negative, meaning above x equals 0 meters. So, you can think of this again as rebounding to some other point 1 minus square root of 5 over 2, and then the cycle continues again. So, the body initially dropped on this little foam, reaches the maximum velocity at x equals half a meter, back to 4 meters per second in the downward direction at 1 meter, because this is the time when the spring or the foam is beginning to decelerate the body, and then it reaches a different point x naught given by 1 plus square root of 5 over 2, where it is completely brought to rest, and now it begins to accelerate in the upward direction. So, the velocity becomes negative. So, if you ask the question what is the velocity of this body at 1 meter, it could be either moving in the downward direction or in the upward direction, and therefore, you have the you are unable to completely resolve the direction of the motion from a work energy kind of an approach. So, essentially you do still have some ambiguity on the direction of the motion if you choose to solve problems using work energy approach, especially because in this particular case the force field is given by 128x, which is a conserved force field. So, as you will see, this body continues to execute this kind of a periodic motion forever. So, it reaches again the point 1 minus square root of 5 divided by 2 as the highest point, and then it begins to again decelerate due to gravity or decelerate or accelerate due to gravity down in a downward sense and the motion repeats. Okay. So, this kind of a problem where you know the force acting on the body as a function of x requires work energy formulation. If you choose to convert this to time coordinate and use impulse momentum, it would either be not possible or very difficult. We will talk about that if we have time towards the end of the next lecture as to under what conditions that inversion is possible. But for now, this is a very useful way to understand the overall change in the kinetic energy of the body with leaving some ambiguity in directions of motions, which is going to be the case in all these kinds of problems. We will continue this discussion in the next example problem.